Today's video will explain how the allocator and the allocator traits work in C++. Hello, I'm James Helfrich. In order to understand how the standard template library vector works, we first have to understand the allocator and the allocator traits. Both of these are an integral part to how C++ optimizes on memory management. We will start with a simple scenario of creating an array of 99 elements. Here I create an array of 99 integers using the built-in array as a stack variable. Unfortunately, this does not really tell me that much about how the array is stored or freed. Let's try something new. I've created my own class called spy. This is a spy double whose job it is to count the number of times various things are called. As you can see, when the default constructor is called, then I'm going to increment a counter. I'm going to do the same thing when a move constructor is called, and I'm also going to do the same thing when a destructor is called. And then I have created a collection of methods which will allow me to query how many times the various things have called. Let's add this to our program. Okay, notice how I had to pound include my spy.h. Notice how I had to initialize my counters because the counters are static member variables in spy. Notice how I called my number default and number destructor. Then I'm going to allocate 99 elements. Then I'm going to report what happens after, and I expect to have 99 constructors called. Now, when I fall out of scope, I expect to have the same 99 constructors already called, and now I'm going to have 99 destructors. Let's make sure this happens. Notice how before anything happens, I have 0 constructors. And then after I have 99 elements created, then I have 99 instances of the default constructor called for spy. Then when I fall out of scope, then I have 99 destructors called. Okay, let's do exactly the same thing except with new and delete. So the only thing I did here was to change the stack array into a dynamically allocated variable. In other words, I specified when the data is allocated with new, and I specified when it's destroyed with delete, not relying upon it falling out of scope to be deleted. Notice when I run this, I'm going to have exactly the same results as before. So each of the 99 elements is constructed when I say new, and each of the 99 elements is destroyed when I say delete. This is exactly what I expected, right? Okay, now things are going to get a little bit spicy. When we call new, two things happen. We allocate memory and we call the constructor. Similarly, when we call delete, two things happen. We call the destructor and we free the memory. An allocator allows us to separate these two things. Okay, let's take a look what happened here. I had to pound include memory for allocate and allocator traits. Just like before, I should have 0 default constructors and do copy 0 destructors called. Now I have to create a new local variable called alloc, and this is of type allocator, and it allocates spies. Now in order for me to reserve the memory, I'm going to call allocator traits decol alloc allocate. Oh my goodness, that's ugly. What this will do is it will allocate enough memory for 99 spies, but it will not actually call any of the destructors. Next, I'm going to go through and call the constructors on the first 33 elements. Notice I'm not going to touch the last 66. Now I'll go through and I'll call the destructor on 33 elements by calling destroy. And then finally, I will free the memory. Let's take a look at what happens when I run this. Okay, just like we expect, no constructors are called, no destructors are called. Now I'm going to allocate 99 elements. Now, even though I reserve space for 99 elements, no constructors are called. Now I'm going to go through and call the constructor on 33 of the elements, and sure enough, 33 constructors were called. Now I'll call the destructor on 33 elements, and sure enough, now 33 are called. And when I free the memory, spy is not aware of this at all. Now you're probably wondering why this is such a big deal. Well, now let's use the spy on the vector. Okay, let's take a look what I did here. First, I had to pound include vector. Now I have a vector of SPI. I expect my size to be 0, my capacity to be 0. I'm going to resize to 10, and that's going to call the default constructor 10 times, so my size and capacity should both be 10, and I really hope to have 10 default constructors called. Now, when I reserve 99, my current buffer is not big enough, so I take the existing elements out and move them into another. So this means I'm going to have to use the copy move constructor, and I expect that to be 10, the ones I moved over, and then my old 10 will be destroyed. So my size now should be 10, but my capacity should be 99. When I clear, I'm going to call the destructor on everything that I had created. So I expect to have more destructors called. My size goes to 0. My capacity stays 99. I'm going to push back 1. I just should have one element to my move constructor because I moved it on. And so my size should be 1 and capacity should be 99. And finally, I'll destroy everything. Let's see what happens when I execute this. Okay. Before, nothing, just like we expect. Here we have an empty vector, so I have no constructors. Size and the capacity are 0. I'm going to resize to 10, so that should be 10 default constructors. My size and capacity are both 10. When I reserved a 99, I got to move from the old buffer into the new, so I'm going to move and destroy. Now my size is 10 and my capacity is 99. That's what I expect here. When I say clear, I'm going to call the destructor. So I went from 10 destructors to 20 destructors because I just destroyed those 20 elements, those 10 elements. Notice how my capacity stays 99. When I push back 1, now my move constructor gets called 1. My size is 1. But notice how I did not have to reallocate because I'm using a spot that was previously unallocated, but now I had to construct it. And when I destroy everything, then everything I created before, including one extra element, will get destroyed.
So why are we talking so much about the allocator? Well, the answer is this. C++ is all about performance. The standard template library, doubly so. The allocator gives a programmer complete control over when things are allocated and when constructors are called, destructors are called, and memory is freed. No other language gives us quite this degree of power, which is essential if you want to have this degree of performance. You can learn more about the allocator in Appendix 1 of the C++ Data Structures textbook.